well, let's see. Is there anything I need to tell you before we start today? I don't think so. I'm hoping to finish the chapter 5 discussion today. So we really have 2 more topics, but they're kind of big ones compared to the ones we were talking about yesterday. And they still have to do with this time dilation formula and ways to misunderstand it or be confused by it as we go along. So after today, you should really dig into that chapter 5 homework. You're in a position where you can do all the chapter 5 homework, ask questions tomorrow, and just get that done so you're ready to start thinking about Friday's exam. I'm actually going to see if I can turn off the front because I notice this gets really washed out for the class here. Okay, so we talked about this time. Oh no, the same thing's happening as happened last time. Let me see if I can correct it. No, I guess my pointer is not going to work. I don't know what the difference is, but for some reason, my pointer is not doing what it's supposed to. So I'm going to sit over here at the computer and point with this. We talked about the time dilation formula, which tells us the relationship between the clock duration, a tick duration of a clock, or a certain amount of time elapsing on a clock, as measured from an IRF in which it's moving at a certain speed. And the dramatic effects happen when those speeds are close to the speed of light. That's what t prime is. And it relates it to the usual time t, the time we have to wait for the corresponding duration, tick duration to happen in the frame where we're at rest with the clock. And that, of course, is the same as the amount of time that ticks off on the clock's reading. Okay, and it's got this factor of gamma 1 over the square root of 1 minus v squared over c squared. So it looks much simpler if you just say t prime is gamma t. If you know v, how fast the clock is moving, you can calculate gamma. And so sometimes it's convenient, rather than specifying v, what the speed is of one frame with respect to another, or the clock relative to the observer. Rather than specifying that, you could specify gamma. And if I know gamma is 2, that means the tick lengths as measured when the clock is moving versus when it's stationary differ by a factor of 2. It takes twice as long to wait for a 1 second tick to elapse on a moving clock if it's moving at gamma equals 2 with respect to us. So we talked about some comments to clarify how not to think about this or how to think about it. The first comment was, if a clock ticks once per second, how is it possible that either t or t prime would not equal 1 second? And the answer is, well, it's going to equal 1 second in the case that we're familiar with, where the clock is at rest with respect to us. But it's not going to, or at least we shouldn't suppose it would work as normal, if we observe a clock going by at close to the speed of light. And so in that case, we may have to wait longer than 1 second for a 1 second interval to elapse off. And that's what this formula is telling us. Comment 2 says we shouldn't naively think of this as observing the clock running slowly is as simple as one person watching it go by. Rather, we have to be very careful and have a whole bunch of observers at rest with respect to me as the clock is going by. And each one of us has a synchronized clock. So we've all synchronized our clock. They're ticking off in lockstep. And as the clock passes by each observer, you make a clock reading that it is reading and your own clock reading. Record those pairs as it goes along, and you can see which one. After the fact, everybody can get together and discuss all that data and see which one was ticking more rapidly or more slowly with respect to the other one. So when we say someone watches a clock go by at high speed, we really mean they have a whole collection of scientists or observers that are in the same inertial reference frame as them, all with their own set of synchronized clocks, and they're all making independent measurements. That just makes life a lot simpler because we don't have to correct for the travel time of the finite speed of light for the signal coming back to a single observer. And then comment 3 was an objection that the light clock is just a bad clock since it runs slowly when it's moving. There's something wrong with it. And the answer to that is, well, you can make a very easy argument with the principle of invariance of coincidences that says that if the light clock runs slowly, then every other clock runs slowly. Every other process, biological, psychological, all of them run slowly. So time itself, we would say, is running slowly compared to the person who's observing it, right? And I guess we ended right at the end of last time where I was saying we should do the first 3 sections of a worksheet, the second worksheet, and I just emailed them out to you Zoom folks. So if you haven't printed it out, that's fine, but just take it out. We're going to do the rest of them, parts D and E, a little bit later after we've had a discussion. But I think right now we might be able to figure out parts A through C without getting confused if you don't think about it too hard. If you start thinking about it too hard, you might find it confusing, and that's good for now because we're about to get into the resolution of how to get unconfused. So let's do problem 1, parts A through C. And for the Zoom folks, just like yesterday, I thought that worked pretty well. I'm going to put you in a breakout room so that you can freely discuss the worksheet together and you don't have to feel like you're on the speakers in our room. So I'm going to throw everyone into the same breakout room and I may come check in a few minutes. Notice that part 1 of this worksheet is just throwing you into the idea of light years so that it's a distance, perfectly reasonable distance, but there are nice ways to simplify your life, and I'll tell you about that when we discuss the worksheet. But I think if you just do it in the most straightforward way, you'll find it works out. The answer to part A is 11.63 years. So for comparison. in the classroom. How are you guys doing on A? Okay. We just need to think about what light year means. It's the distance light travels in 1 year. I'll show you an easy way to deal with that. And it looks like, see, Jacob is still in the breakout room, so I'm going to wait for just a second. See if this is still malfunctioning. Nope. Weird. Okay, so let's discuss especially part A on problem 1. We're told that Earth and the sun we're going to consider to be in the same inertial reference frame in this case, and they're traveling to one of sun's nearest neighbors, star neighbors, Procyon, and the speed they're going at is 0.98 c, and we actually worked out what gamma was for that last time, although you could have done that from scratch in part B. Gamma is 5.025 or 5.03 about. Okay, so in this case, we can work out what gamma is again from scratch, but it's 1 over the square root of 1 minus v squared over c squared, or v over c squared, and v over c is 0.98. So we need to square that under the square root, and that's very close to 5.03, and I'm just going to use that in the later parts of the problem. We don't need it in part A. Okay. As measured, okay, and we're told that Procyon has been measured by scientists on Earth. In other words, in the Earth Procyon, that we're assuming those two, Earth and the Sun and Procyon, are all at rest with respect to each other. So they're in the same IRF, whereas the spaceship is in a different IRF. And from the point of view of the Earth, Sun, Procyon IRF, where they're all essentially at rest with respect to each other, they measure Procyon to be 11.4 light years away. 1 light year is the distance light travels in 1 year. And that's a very common unit of measurement for astronomical observations, just because, you know, it's an easy thing to think about how, you know, over great distances, how long it would take light to go a great distance is perhaps not that long. A, as measured by observers and clocks in the sun's IRF, how long does the spaceship's trip to Procyon take? Well, we know if the ship were traveling at the speed of light, as measured by the Earth and the sun's IRF, we already know it should be 11.4 years because the distance is 11.4 light years. But they're not going quite that fast, so we need to use the fact, our old friend that we're using quite a bit these days, and we'll continue to use quite a bit. Distance equals speed times time. Okay? The distance they have to travel is 11.4 light years. So let's write down 11.4 light years. And I'm not used to that unit light years, or at least you're probably not used to it, but I can think about what a light year is in terms of, again, distance equals speed times time. 1 light year, all right, that is 1 ly, ly being short for light year. That distance is equal to the distance light travels. And so light travels at speed c, and the time that elapses is 1 year. So I can always replace 1 light year with c times 1 year, and we'll find in this case that actually simplifies our calculation because we won't have to end up putting c in here anywhere. So instead of putting light years here, I'm going to put 11.4 c times 1 year. Okay, that's the distance it has to go, but I've written that unit of light years in terms of speed times time. Okay, now the speed that the ship is going at, that's this speed, is 0.98 c. And the time is what we're after. So I'm just going to leave that as a t over here, and we'll solve for t. The nice thing is I didn't have to put in 3 times 10 to the 8th for C because there's a common factor of C on both sides. And so the C just disappears. It wouldn't hurt if you put it in. It's just more typing in your calculator on both sides, or you might have seen it canceled even if you wrote it out. So that means when I solve for T, I just need to divide both sides by 0.98. So that's 11.4 over 0.98 times 1 year is equal to T. And so when you divide by a number that's bigger than 1, it makes it smaller. When you divide by a number that's smaller than 1, it makes it bigger. So it's going to be a little bit more than 11.4 years. It's actually 11.63 years when you calculate it. Okay? Any questions on A? Speak up if you got one. Yes. You know, I'm willing to be very forgiving as long as you're getting the correct answer. And so if you're able to do that stuff in your head, that's fine. For most people, I think you might want to, especially when you're dealing with something unfamiliar like light years, to actually write out C times years, you know, and so maybe it takes 2 lines instead of 1 line of writing. That's still. Well, I'm trying to explain it in a way that everyone, regardless of where they're at algebraically, is going to be hopefully comfortable with this kind of stuff. Now, that doesn't mean that if you're someone who does algebra all the time, you may do these gymnastics in your head. And so, but, you know, there's always, sometimes people try to do too many things in their head and then they get it backwards or flipped around and get the wrong answer. And then if they don't show it, if it's on an exam, I don't have the means to give partial credit because all I see is an incorrect answer written down. So sometimes it's to your advantage to try to show what your reasoning is. Okay, B, as measured by the observers in Earth's IRF, how long does it take for the clocks on the spaceship to elapse by 1 year? So this is a direct question related to the time dilation formula, right? So I'm going to write down the amount of time the people on Earth have to wait for a moving clock, the clock that is in this ship, to elapse by 1 year, is equal to gamma. Gamma is 5.03. That's our gamma. Times T. And, you know, we want T to be 1. Sorry. Let's see. Yes. This is the amount of time we want to elapse in the frame that's moving along with that clock. So we want that clock to elapse by 1 year. And we know the people on Earth are going to have to wait a longer time, right? So this T that I want to put in here is 1 year. And that means the people on Earth are going to have to wait 5.03 years because gamma is sort of stretching out, dilating time by a factor of 5.03 between the 2 IRFs in this case. Questions on that one? Okay, C. By how much will the crew on the spaceship age during their trip to Procyon? Well, their clocks, as observed by the people on Earth, are running slowly. And that means if their clocks are running slowly, they're going to age less. So in this case, it takes, according to people on Earth, it takes them 11.63 years. It's going to take them less time. And in fact, think about the relationship between this time dilation factor, gamma. This tells us that it takes longer for the moving clock's tick to elapse as measured by people in the frame in which it's moving. If it takes longer to elapse, that means the time that is experienced as having happened will be correspondingly less. In other words, if the clock ticks off at a factor of 2 slower, right? In other words, if this is a factor of 2 right here, then the time experienced by the people on the ship would be 1/2 the time that's experienced by the folks on Earth. If it were a factor of 3 here, it takes 3 times as long to tick off the corresponding amount of time. the people on the ship would age 1/3 the amount as the people who are on Earth. So if it takes 5.03, if gamma is 5.03, then that means the amount of time that's experienced, I don't know what a symbol is for that, but the answer to part C would be, if the tick length is increased by this factor, then the time experienced is decreased by that factor. Now, the time experienced by those on Earth is 11.63 years. That's what we figured out in part A. The time experienced by those in the spaceship is going to be correspondingly smaller, and the correct factor that you cut it down by is divide by gamma or multiply by 1/gamma. That's a little bit confusing because the tick takes longer to occur, but the amount of time they experience psychologically, physically, biologically in the ship is going to be smaller. And so we've got to divide by that corresponding factor of gamma. You have to think about that a little bit to make it clear. In any case, this ends up being 2.31 years. And that's a real effect that, at least probably technologically we couldn't achieve this now. But in principle, it's something that we could verify. In other words, we have two widely separated distances and have something travel at a very high speed between them and actually have them carry a clock along with it. And you could see, wow, you should be more than a decade older, but you've only aged by a couple of years. Or you carried an atomic clock along with you. And so we have a very precise measurement of the amount of time. And wow, a lot less time ticked off on that clock. You carried it along with it compared to the ones on Earth. So this isn't just an imaginary effect. It's an effect that can have real consequences. If you were imagining a future where space travel, to really distant locations were important, this could be a really interesting effect because it means you can send someone to a place that's horrendously far away so that, it might take 300 years as judged by people on Earth to get there. But if you travel fast enough, maybe only 1 year elapses as judged by the people on the spaceship. So they make it and they still got, a good long life to live at the other location, assuming it's a friendly place to be. Okay, any other questions on that before we go back and do our last big comment, which addresses some of your reading responses and other concerns too. Let's see, share screen. Okay. And let's go back to here. That looks good, I think. And just to not have this be awkward, I'm going to move this back a little bit till we need to work on the board some more. Okay, let's look at a few of your reading response items. This chapter was a little confusing for me as well. This is, referring to somebody else's comment that came before. Oh, good. Now I've got my laser pointer working. I had to go back and reread it a lot. Yes, it's getting to that point, and you're going to find the same thing is true in the next chapter and the chapter after that. They derive results that are going to require a little bit of algebra, referring back and forth between equations and figures. There's nothing terribly complicated, but it takes some effort to follow it. So you're not alone if you're feeling it was confusing in that particular way. The only way I can reconcile this, I can't remember what came before this, but this counterintuitive effect that they're referring to is by suggesting that we do not consider the light beam clock as a clock, but just something to be measured. What do you say about that compared to our discussion from last time? In other words, the only way to make sense of this is say, the light beam clock's not a real clock. It's, of course, with something we can make measurements on, and it might slow down as it's moving faster, but at least it's not a real clock. That's the only way to make sense of it. That was the subject of that third comment that we did right before the end of class last time that said, if this light clock or light device, if you don't like calling it a clock, runs slowly, everything's going to run slowly because its up and down bounces can be correlated with the positions of a clock. And by the principle of invariance of coincidences, those things are going to correlate no matter how people are moving with respect to each other. So if the light clock goes slowly as observed by someone when it's moving by, the regular clock's going to move slowly. Neural processes are going to go slowly. Biological processes are going to go slowly. Movement is going to go slowly. Everything slows down. There's nothing that's not affected. So I would say, yes, it's tempting. And in fact, Merman says, yeah, you know, a lot of people object and say it's not a good clock. No, it's a perfectly good clock. It's maybe not the most practical clock, but it is useful to derive these effects. But once you've derived them using that clock, it's a perfectly good clock, and it's going to correspond to the behavior of all other clocks, for which it might be more difficult to see the special relativistic effects. Third comment, I'm also interested in how observer A and observer B would each say the other is slowing down if they consider themselves to be the observer at rest. This violates the principle of relativity. Well, I would say no, first of all. It doesn't violate the principle of relativity. If that were not true, it would violate the principle of relativity, right? A and B are in completely symmetric situations. A sees B moving at, A is Alice, so A sees B moving at her at 0.98 C. That means Bob sees Alice moving at him at 0.98 C too. Completely symmetric when you switch frames. They're performing the same experiment. If they didn't, oops, that's not what I wanted to press. If they didn't observe the same outcome, which is to say the other one's watch is slowing down when I make careful measurements of it, that would be a violation of the principle of relativity. So we need this to be true in order for the principle of relativity to be satisfied. But this person is saying that's completely confusing, and Merman somewhat unsatisfyingly says, time can have different meanings for different observers, and this person is saying, I'm not sure this is sufficient. No, it's not sufficient. We're still in the middle of this confusion. We're only beginning to sort it out. We're going to address this actually right now, although Merman doesn't address this issue. You really don't get to the point of it until chapter 7. But I'm just going to give you a little preview now in order to not make it seem so confusing right now. Okay. So the principle of relativity says, if your clock moves more slowly than mine, then mine has to move more slowly than yours because we're moving at each other in a symmetric way. Is there a paradox there? And let me find, I had some other comments here that I wanted to make sure that I said. Yes. You age more slowly than me. I age more slowly than you. How can we make that make sense? Several of you have brought this up. One thing that it sort of helps us out a little bit at this point of view, or at this point in the discussion, is that it's difficult to compare ages unless one person, if we're both aging more slowly than each other, as judged by the other person, we can't really directly compare unless we come back together. And we're going to discuss something in a later chapter, I think at the end of chapter 7 is the first time we visit it, called the twin paradox, where we actually do that. Someone stays on Earth, someone goes at a high speed to a distant planet and then comes back, and they actually do compare their ages, and they don't match. The amount of time that's elapsed isn't the same. But as long as the two are just moving past each other, it sounds paradoxical. It sounds like a logical contradiction if we say, B's clock runs more slowly than A's, and also A's clock runs more slowly than B's. But perhaps a more careful way of stating it is that B's clock runs slowly as observed by A, and A's clock runs slowly as observed by B. And there's no logical contradiction in those because they're two different points of view. The measurements are taken from two different perspectives, so we can't directly compare them. They're not contradictory unless, of course, you're assuming that judgments about time and how long something takes are agreed upon by everyone. And in this case, they're not agreed upon by everyone. So we're only seeing actually one of the pieces of this. And Merman's point here is just to point out there's no logical contradiction when we think of it as two different perspectives. We can't map them onto each other directly. I have a note here that says it's like a group of people. So I have the vague memory that I was hearing this may be apocryphal. I can't remember if it was pygmy tribes in, Central Africa, or if it was Amazonian tribes or something early on when they lived in the dense forest and they could never see anyone really far away. It caused some confusion when they first saw clear cutting come up to the edge of their territory, and they came up there and they could see someone far away. Now, they might think, hey, there's George over there. George is really small compared to me. And he talks to George, and George said, no, I looked at you. You were really small compared to me. That sounds like a logical contradiction. But in that case, no one would say that there's a contradiction. It's just a different perspective that each person has. So we'll hold on to that for now and try to elucidate, make this seem like more of a paradox. So let's dig into it deeper, because it still seems like there's going to be a contradiction if we consider definite time intervals between specific events. So let's imagine here's Earth here, here's some distant star, maybe not so distant star, but we could think of it as Procyon in that example. And we're going to send someone at a great speed, in this case gamma equals 2, just so that I can easily do the calculations in my head. That means the time intervals experienced and the clock tick rates will differ by a factor of 2, so that's kind of convenient. And let's identify some definite events that everybody can publicly identify. Event 1 is frame B leaves Earth. Right? So right when B is passing by Earth or something, we're going to assume they go at a constant speed. So maybe it's when they first pass by Earth. Event B is when event 2 is when B passes by this distant star. Everybody can look at and identify those events. Okay? Let's imagine a conversation about people who knew a little bit of relativity and how they would think about these. Or, A makes some observations. So A says, from my point of view, I see my scientists took measurements, and it takes you 8 years to get there. So your clocks run slowly, and therefore you, B, are going to experience only 4 years because your clocks are running slowly. Okay? This is after the whole trip is done, or maybe when they're still doing the calculations and they're not sure about it. Okay? They're running slowly because gamma is bigger than 1. Gamma is 2 here, and that means the tick length from the point of view of Earthlings, that's the one in which the ship is moving, the ship's clock takes twice as long as it does for the corresponding clock on Earth to tick off a year or whatever. So it takes you 8 years to get there. Your clocks are running slowly. I can see that. So you're going to experience only 4 years. B says, yes, it only takes us 4 years to get there. We did the experiment, and that's what we found out. Now, I looked at your clocks while we were traveling there, and they were also running slowly. So you will say it's only going to take me 2 years. And that seems like a problem. Of course, A comes back and says, no, your clocks run slowly. I already said it takes you 8 years to get there. You didn't hear me before? It can't take you 8 years and 2 years. So that sounds like a contradiction. It's going to take some effort to work out why there's some misapplication of the time dilation formula here that we haven't learned about why it's a misapplication yet, okay? Seems like each one sees the other clock as going slowly, and that in fact is true. But that doesn't mean we can directly compare the time intervals that each will measure without thinking a little bit harder. So why isn't the situation symmetric between A and B here? Okay, so here's our two events. The ship leaves Earth and the ship arrives at the distant star. The key difference between the 2 points of view, the Earth star IRF and the B IRF, is that, from the point of view of A, someone on Earth and the star are at rest, and A's clocks at those locations, of course, A is going to have whoever's clock is near this distant star. They've got a co-scientist over there, and they're going to have their clocks be synchronized with respect to each other. So they're actually ticking off in lockstep. They read noon at exactly the same time. They've worked very hard to make sure that they could do that. They could do it with light beams and knowing how fast light travels, and then setting the clock ahead by a little bit. Okay. Now, the important thing is that the difference between these two that we're going to see is that there's only one B clock, the clock that's inside the ship in B, that's present at both events. That clock is present when the ship leaves Earth, and that same clock is present when the ship passes by the star. Probably doesn't land on the star. Okay? And that clock is seen to tick slowly, and since it started out at the first event, and it ended up at the second event, and it is moving slowly the whole time, it's certainly true that the amount of time that's experienced by A, the Earth frame, is going to be greater than the amount of time that's experienced by B. That delta in mathematics is used to indicate some elapsed amount of time. So delta T means how much time elapses between those two events, as measured by A and as measured by B. Right? B's clock was running slowly the whole time, and they were there at A, and they were there at Earth, and they were there at the distant star. So B is definitely going to experience less time. That's true. What's wrong from the other point of view? Uh-oh. I'm not sure what happened there, but somehow my fancy new pointer is not doing so well. What does B see as B is traveling? Well, of course, B is in an inertial reference frame. They feel perfectly at rest. They're sitting there at rest. Earth is rushing away from them. Stars rushing toward them. I guess from this point of view, they're going in that direction at gamma equals 2. Okay? The important difference is that there are, in this case, 2 different A clocks that are present at the 2 events in question. There was one clock on Earth that was present when B left Earth. And there's going to be another clock over here near Procyon that's going to be present when B reaches Procyon. Okay, why is that important? We're going to find out in chapter 7 that if A sees these 2 A clocks as synchronized, in other words, A, of course, IRF-A, there's many people in IRF-A. There's an observer on Earth, there's an observer on Procyon, and A is, of course, going to keep their clocks synchronized. That's only sensible that we would want to do that. If that's the case, then B will see the clock at the star, we'll see the 2 clocks as not synchronized. And in fact, they're not synchronized in a way such that the clock on the star here is ahead of the clock on Earth. Okay, so things that are synchronized in one frame are asynchronous in another frame. Okay, so if A says my clock reads noon right when the Earth people and the star people clock read noon at the same time, and they read 12:15 at the same time, B is going to have a different opinion about that. B is going to say at any given, you know, what I'm talking about B, of course, we have to think about observers moving along with B. There's really a whole line of observers that are all moving together, and they're taking careful data, and they can see that these 2 clocks at any one time, because all of B's observers are going to have their clocks synchronized, and they're going to say, right when all our B clocks read noon, record what the one at whoever's near Procyon, you record what the reading on the Procyon clock is. And whoever's near Earth, you record what the reading on Earth clock is. And then we all come back together and we find out they're different at that time. So at a time that's simultaneous for B, those A clocks are not going to be synchronized. Okay? So how does that affect what's going to happen? Well, the observed lack of synchronization of A's clocks in B, okay, so A is the Earth Procyon system, is going to make B realize that even though A's clocks are running slowly as observed by B, right? B is flying by Earth and saying, Earth's clock is running slowly there, and as they're coming up on Procyon, Procyon's clock is running slowly there. Still, A is going to judge the time interval to be longer than B when she uses the local times on her clock. Why? When B left Earth, one of B's friends who's moving along with B, who happened to be over at Procyon, would say, wait a minute, that clock is 15 minutes ahead. So even though only 5 minutes elapses on this journey, they're going to say when they compare the data, right? Well, you left at noon. 5 minutes elapsed according to B seeing their clocks running slowly. Maybe it takes 5 minutes to get here. the ending time is going to be 20 minutes after, because 5 minutes has elapsed on this clock by the time they get there. And so they'll actually say it takes longer. Okay, let's do that again. It's very confusing. Let's do an example with numbers, kind of the numbers I was just saying. Okay, so Earth and the star are not moving with respect to each other. They're in the same IRF. B is moving relative to Earth at gamma equals 2, leaving Earth and arriving at the star 10 minutes later. So let's imagine this trip. This would have to be almost as close as the sun, but let's just take the numbers at face value. So let's say this trip takes 10 minutes according to B. According to B, the clocks on the ship, they tick off 10 minutes. In A, in the Earth-star inertial reference frame, they have clocks at both locations, and of course, in their frame, they keep them synchronized. But in B's moving inertial reference frame, if these two clocks at the star and the Earth are synchronized in the star-Earth frame, they're not going to be synchronized in the moving frame of B. And in fact, in B's frame, the star's clock is going to be ahead by 15 minutes of the one on Earth at every time. They're both ticking ahead in lockstep slowly, but one's always 15 minutes ahead of the other one. Okay? Now, in B, it takes 10 minutes for it to for B to get from from Earth to the star. Okay? And B still sees those clocks running slowly, so they only tick off 5 minutes of time because they're going in at gamma equals 2, right? If B observes it taking 10 minutes to get there, they see the Earth clocks as moving at gamma equals 2, so they're only going to experience 5 minutes of time elapsing during that time. That doesn't mean that A is going to say the trip took 5 minutes, right? Let's suppose they leave at noon, right? And A says, okay, ship left, it's noon. And then at that particular time, according to B, it was already 12:15 over here. The trip took 5 minutes or at least 5 minutes of time elapses on the clock, as observed by B, elapses on this clock. So this one moves from 12:15 to 12:20, and they're going to say it took 20 minutes to get there, which is exactly the time that they should say, right? Because if, according to the Earthlings, B experiences less time, then B should say, when A's clocks on Earth and Procyon, when they get back together and look at the data, they should see something that took longer, even though the time dilation formula seems to always say it takes less time. That's because of this asynchronization property that we will derive in numeric detail in Chapter 7. But for right now, that's just a warning that there are other things that we need to take into account, okay? This is what I just said. The important thing I was going to say here is that the time dilation formula doesn't know anything or say anything about this asynchronization of clocks in a moving frame. So you have to be careful if you're talking about the time interval between two events. If those two events have two different clocks on them, the time dilation formula, even though those clocks will be running slowly from the point of view of someone zooming by, right? As they're zooming by that person, they'll see the clocks running slowly. They're not synchronized, and so we can't just naively conclude how much time will have elapsed from that person's point of view between the two events. However, we can do it from the point of view where B is the one is moving. In other words, A's point of view doesn't have that problem for correcting between a lack of synchronization of the clocks that are moving, because there's only one important clock, and that's the one on the ship here. B's clock was present at the Earth, and later on that same clock in the ship is present at A. So we don't care about it's true that B's clock on the ship, somehow it doesn't like it when I'm too close there. Got a malfunction again. Somehow it is true that, from A's point of view, B's clock here on the ship and one of B's fellow scientists who's still zooming at gamma equals 2 in this direction, but is somewhere else over here. From A's point of view, from the Earth's point of view, those two clocks wouldn't be synchronized either. But we don't really care in this experiment because the two events we're trying to compute the time interval between only involve one clock measurement in B. So the fact that B's clocks are asynchronous doesn't come to anything in here. So in summary, and I know this is a lot to kind of swallow, but we're going to investigate this in more detail in Chapter 7. We can use the time dilation formula to compare the time interval between two events as seen by two different IRFs, in other words, the Earth view and the ship view here, without having to correct for clock asynchronization, but only in the limited case where in one of the IRFs, the events occur at the same location. That would be the ship point of view, right? The two events we're concerned with occurred at the same location. And there's one clock that's present at both those events. And so we don't need to worry about comparing the reading of two different clocks. And therefore, the asynchronization doesn't matter. Okay, so we've got to have one clock that's present at the two events if we want to apply the time dilation formula naively. And the time dilation formula has to be used in the sense where that clock that's present at both events is the moving frame. In other words, in the time dilation formula, they're the ones that are doing the moving, and so they're the ones who are going to experience less time because their clock is slowed down. If you apply it in that way, you will be correct. You can't apply it the opposite way. You'll make kind of, if you don't think about it carefully, you'll make the exact wrong conclusion. Okay, and again, the idea that if we take it from the point of view that the ship in this example is the moving frame, it's going to take longer, as observed by Earth, for the ship to tick off, say, 1 year than it will for the Earth clocks to tick off 1 year. But that doesn't mean the time elapsed is longer. The time elapsed is correspondingly shorter. Okay, gamma is greater than 1. If the ship's clock ticks take longer, that means the ship experiences a correspondingly shorter amount of time. So you could say this is an equivalent formula that could be applied in this case. The amount of time that's experienced in the moving frame, in this case, is going to be greater than the amount of, less than the amount of time that's experienced in the frame that's at rest from that point of view. When you divide by gamma, gamma is bigger than 1. So if the people on Earth say, oh, exactly 1 year elapsed from the point of view of the people on Earth, and gamma is 2, then the people on the ship will say exactly half a year elapsed. Okay, I know that's quite a bit. So in summary for this comment in 4, your clock moves more slowly than mine. Mine then must move more slowly than yours. That sounds like a paradox. And it is true as measured from each of our own inertial reference frame that the other clock always runs slowly. But the comparison of time intervals between events is complicated by the facts that, of course, when a bunch of people are in my IRF, we all synchronize our clocks. That's only natural. But that's the best we can do. We can't have them synchronized from other people's points of view. The time dilation formula doesn't tell us about this lack of synchronization, but we can compare the time interval between two events as measured between two different inertial reference frames in the special case where a single clock is present at both the events we're interested in. In other words, that kind of means that one of the clocks just passes by the first event and then it happens to arrive at the second event of interest just in time, like, or it's defined by where it arrives later on, as it was in the example. Okay, and in that case, the shorter time interval experience will belong to the inertial reference frame in which the events occur at the same location, the one that we think of as moving in that picture, right? If we're comparing Earth's point of view to something moving, it's that moving point that's going to be present at both events, okay? And what that tells us is that the smallest time interval between two events is always experienced by the inertial reference frame in which they occur at the same location. And so that's given a special name, the proper frame, and this shortest time interval that can be experienced between two events by, if you compare all the different IRFs, the shortest time interval is sometimes called the proper time interval, and that's the interval experienced by a person who's present at both of the events in question. Okay, now, I don't want you to lose focus on this because, yes, it's true. If we want to apply the time dilation factor to compare time intervals, we have to be very careful about them. But we shouldn't make that shouldn't make us lose sight of this amazing fact that I've written up here. The time interval between two events depends on the IRF from which they are observed. That's something that Newton wouldn't even know how to think about. All of our intuition about time tells us that if one person measures 2.3 hours between two well-defined and publicly identifiable events, everyone should measure 2.3 hours between them. If they don't, we'd think they've made a mistake. Okay, this intuitive view of time intervals is called universal time, the assumption that everybody's time is sort of ticking off in lockstep, never at different rates. Okay, all historical thinkers who had a coherent notion of measuring time agreed with Newton until Einstein. Okay, so an understanding of relativity is going to show us that there's nothing inherently inconsistent about non-universal time. And we have to take into account both the time dilation effect and the asynchronization effect to get the idea that there's no contradiction there. Okay, and we're going to see other strange and non-intuitive effects arising from the principle of relativity and the principle of constancy of speed of light. This is just the first interesting one that we've seen. So I want you to go and finish up the worksheet now. The idea here is we stopped at C, we sort of applied the time dilation formula without thinking too carefully about it. And now we realize if we're going to switch to the point of view of, if we want to ask by how much do people on Earth age as the ship goes to Procyon, you might be tempted, if you hadn't thought about this, to say that, well, it's going to be less than whatever we just calculated for the amount that the people on the ship age, because their clocks are running slowly. But we know that's not true. It actually goes the other way. The people on Earth are going to experience a longer point of view, a longer elapsed time between those two events, the ship leaving Earth and arriving on Procyon. So try D and E. I'm going to put the folks on Zoom quickly in a breakout room just so you can discuss a little bit, and we'll pull you back in a couple of minutes to finish discussing those. You'll find that we've actually already given the answer to D. The only thing is to not be tricked. E requires a little bit of algebra to figure out how fast someone would have to be going for a certain effect to take place. Okay, I'm letting them know that the rooms are closing now. D is supposed to be the easy part of this. E requires some real thought, and we'll do that one together as soon as everyone's back here. Okay, let me see if I can get this all in here again. All right. So what's the answer to D? Somebody just shouted out. You really don't have to do any work to answer D. You'd be doing some work if you applied the time dilation formula and used the fact that from the ship's point of view, Earth's clocks are running slowly, but we now know that's incorrect. You have to take into account the synchronization of, or lack of synchronization of the clocks in that case. So rather, the answer to D is the same as the answer to A. We already figured out how much time elapses on Earth while the ship goes from Earth to Procyon. So the answer to D is just simply 11.63 years. No more work to be shown there. The only possibility is that you would have confused yourself and thought it should be less than the answer right above it, less than 2.31 years. That's not true because of the asynchronization of the clocks. Now, E, the reason I pulled everyone back so quickly to talk about this is because E requires a little bit more work than maybe we're used to doing, even though it seems harmless enough. Well, okay, here we were given 0.98 c was the speed of the ship relative to Earth. What different speed? Let's forget about the 0.98 c. And what different speed relative to the sun would the spaceship have to travel to Procyon so the crew experiences the trip as lasting 1 day? Now, it's going to have to be pretty fast. They already experienced it as 2.31 years, but we want that 2.31 years to be exactly 1 day, or 1/365th of a year. So presumably, I'm expecting something much, much larger than 0.98 c. It's going to have to be really close to c, but we can make the effect as big as we want. So what I'm going to do to explain this is just sort of I'm going to erase some things in our work that we've done up here because we don't know that this is 0.98 c anymore, right? So if I want to calculate how much time elapses from the point of view of the Earthlings, right? That's what we were trying to calculate here. From the point of view of the Earthlings, we knew the distance that the ship had to travel from Earth to Procyon, and that was the speed times the time, and we're using all of those in the same reference frame. So distance equals speed times time is fine to use as long as you're using the distance and the corresponding time are measured from the same reference frame. There's no adjustment to that in relativity. They've just got to be measured from the same reference frame. So the distance they had to go was 11.4 light years, and we wrote that as c times years, and that's equal to the speed they're going. They're no longer moving at 0.98 c. Now there's some unknown value, v. Well, in fact, we could write it this way. We could leave the c that we had in there and put a v over c there, right? Maybe that's the easiest thing to do. And that way I can still cancel out this factor of c right here. There's still a common factor of c. But I have an unknown v that I've got to put in there. Exactly how much time the Earthlings say it takes the spaceship to get to Procyon depends on how fast it's going, of course. There's nothing particularly relativistic about that formula that we're applying there. Okay, now, so what that means is what this number is here, this 0.98 is our v divided by c, right? If they're moving at 0.9 c, then if we divide by c, that would be 0.98. So instead of having a 0.98 in the denominator, we're going to have a v over c in the denominator, and a v over c in the denominator, hopefully this isn't too much of a stretch, is the same thing as a c over v in the numerator. I'm just trying to simplify my formula. So if I solve this for t, the amount of time as seen by the Earthlings, we would get a factor of c over v in the numerator there, okay? And now we want to know if the Earthlings experience this much time, how much time is experienced? Well, this tells us how the tick lengths compare. In order to compare the time intervals, we had to divide by gamma, right? If gamma is big, 1 over gamma is a small number, and that's going to make the time interval experienced much smaller. Okay, so let's take this result here and plug it down into this formula. So this t ended up, in this case, the 11.63 years was the result of this. Now it's going to be something different. We don't know that that 11.63 is valid anymore. So I'm going to replace that 11.63 with the result that we have here. 11.4 times c over v times 1 year. Okay? And this thing in the denominator, remember, this is a gamma in the denominator. Gamma is 1 over the square root of 1 minus v squared over c squared. So 1 over gamma, which is this, is just that same square root in the numerator. Perhaps this problem is maybe a little bit too confusing. Okay. So dividing, when you multiply by gamma, you get this thing in the denominator. When you divide by gamma, which is what we did before, we get this thing in the numerator. And we don't know that gamma is 5.03 anymore. Now it's something unknown, but we've got to compute it with this square root that comes into the definition of gamma. And we want the result. This is not necessarily the result. We want the result to be 1/365th of a year. Okay, and now I can just solve that equation. That was by far the hard part, setting that up. I wouldn't give you something like this on an exam. Those 2 steps of putting in the unknown v and then having to solve it just seems overwhelming. We can figure it out. I can cancel out the years on both sides and then just start thinking, well, how would I solve this for v over c? Well, probably the first thing I would do is square both sides, right? To get rid of the square root. We talked about that before, right? And then I would multiply this c over v times those things that are in there. And after the dust settles, let's see. Maybe, I guess the way I had it is looking something like this. If I solved for that square root on the left-hand side, I would get the square root of 1 minus v over c squared. That would be equal to v over c. I'm multiplying by the reciprocal of this on both sides. We'd have to divide by 11.4, and we still have 1/365, and the 11.4 is going to go in the denominator as well. And we could combine those numbers together. And now I'm going to square both sides and solve for v over c. And maybe because this example seems a little bit excessive, here's what it comes out. If you're not good at algebra, you may not want to attempt that one. V is 0.9999997 c. Well, we knew it was going to be close to c, right? It took 11.6 years from the Earth's point of view, and we're asking it to last only a day from the point of view of the travelers, right? You're going to have to travel really fast to get that big of a time dilation effect in there. Okay. Questions on? Oh, and I'm sorry. I guess I am. I just didn't pin my video on here. Any questions on that before we go to the last topic, which we clearly are not going to have time to finish today, but we can at least set it up and maybe do the worksheet at the beginning of tomorrow. All right. Here's the experimental evidence for time dilation that Merman refers to at the very end. It's just kind of in the last paragraph or so, okay? Here's a few facts. A muon is a particle very much like an electron. It's almost identical to the electron, except it's much more massive. If I remember correctly, it has a mass about 200 times an electron. And it's unstable, so it decays into, this muon will decay into an electron, which can be detected, and also some other particles called neutrinos and antineutrinos, which are almost impossible to detect, so we're not going to see those, but they'll decay quickly into an electron. And the idea is these are being constantly created in the upper atmosphere, which is about 10 kilometers above Earth's surface. Cosmic radiation comes, these high energy particles come from outer space, hit the upper atmosphere, and in that particle interaction, they create a muon. And those muons will travel down toward the surface of Earth, or at least they're going to try to. Now, here's some experimental evidence about unstable particles. These muons, if you could create a bunch of them just sitting in front of you, so they're not moving with respect to you, so we don't have to worry about time dilation or anything like that. If we create a group of them in the lab, half of them are going to decay each 1.5 times 10 to the minus 6 seconds. Okay, that's 10 to the minus 6 seconds is a microsecond. So 1.5 microseconds. I don't know where, Merman puts the number 3 in there, but the accepted number is about 1.56 microseconds. So maybe the experimental evidence was unsure at the time he wrote his book. It's kind of an old book now. That's called the half-life. So the half-life means if I have 1 million muons sitting in front of me, after 1.5 microseconds, I'll have 500,000. And then after another 1.5 microseconds, I'll have 250,000. And it keeps getting divided by 2. Every time you wait another half-life, half of what's remaining is gone. That's the way radioactive decay works. And you can observe that kind of effect in a lab very easily. Just seeing the amount of radiation falls off very quickly as time goes on because there just aren't many left to decay. And typically the ones in the upper atmosphere have a typical speed of 0.98 c relative to Earth. We're going to assume that all of them do, just for the, of course, this real experiment that I'm going to describe is kind of complicated. They have lots of different speeds, but a typical speed is 0.98 c. We're going to assume they're all moving at 0.98 c. And the question we want to answer on the worksheet that we're going to start tomorrow, at the beginning of tomorrow, is if 1 million such muons were created in the upper atmosphere, how many muons would reach Earth? And maybe what I want to do in the last 4 or 5 minutes is together think about how we would do that if we didn't know anything about relativity. Sometimes people call that the non-relativistic point of view. What would Newton say about this, right? If Newton accepted all these facts up here, and we asked Newton, how far does each of these have to travel? How much time is going to elapse from the point of view of an Earthling watching this happen? How many half-lives elapse during that amount of time and the number surviving? We could figure out how to fill in that table in the non-relativistic sense, and then we're going to compare with the relativistic case. So how would I, just to start this worksheet here, and I'll pass out the worksheet next time, what's the distance that these muons have to travel from upper atmosphere to Earth? That's something we don't have to calculate. It's 10 kilometers. That was just given in the problem, so no problem. This distance is 10 kilometers. You'll see when I set this up later, that'll be filled in. How do I calculate how much time elapses from the point of view of someone in the Earth reference frame watching them come down that distance of 10 kilometers? Especially if you're Newton, but actually Einstein would agree with this method. Yeah, use distance equals speed times time. As I say down here at the bottom in sort of a pink font, distance equals speed times time applies only if all three are measured from the same inertial reference frame. But in this case, this distance, the 10 kilometers, is as measured by someone on Earth, and we want to calculate the corresponding time it takes them to get down as measured by someone on Earth. So we could use distance equals speed times time. And when we do that, you get, of course, a very short time because they're moving really quickly. 10 kilometers sounds like a big distance, but relative to the speed of light, it takes almost no time to go that distance. So it takes about 1.5 times I'm sorry. Takes about 3.4 times 10 to the minus 5 seconds to get down. Okay? And maybe I'll finish up with this question. Okay, so we are given the distance. We can use distance equals speed times time to conclude the time it takes as seen by someone on Earth. Again, we're forgetting about relativity for the moment. How many half-lives are going to elapse on the way to Earth from the upper atmosphere? Well, if one half-life elapses, that means we get half of them. We just want to figure out how many half-lives elapse as they're traveling down to Earth. What would I do with the time that I just gave you here and the given half-life up here, 1.5 times 10 to the minus 6 seconds, to figure out how many half-lives elapse? Yeah, we're going to divide them. In other words, one way to think of it, let me just share the camera for a second. Oh, I see. I'm not sharing my PowerPoint slide anyways. So I'm sorry to the Zoomers. Yeah, I'm not sharing my screen. I'm sorry that you guys have been staring at the board unless you enlarged my... So let me put the numbers in here and then we'll quit for today and we'll start setting this problem up again next time to help remind us of it. So in this case, filling in the table that was at the bottom of that slide, we're going to find the distance they have to go is 10 kilometers. Let's write that as 10,000 meters, maybe, right? Using distance equals speed times time, 0.98 c times t, I could solve for t and put in the numerical value for c in meters per second, and we would get the time it takes them to reach from the upper atmosphere to Earth is 3.401 times 10 to the minus 5 seconds. In this case, the half-life, sometimes people label that, of these particles is 1.5 times 10 to the minus 6 seconds. That's quite a bit shorter than this. So there's a number of half-lives that elapse during this time that they're going in there, right? So we could say this number is equal to, I don't know how to write it, the number of half-lives, I'll just put that as the number symbol, right, that hashtag symbol or whatever, times 1.5 times 10 to the minus 6. What number of these do we have to multiply together to get this? And that number that you'll get is 22.7. Okay, so we created 1 million of them in the upper atmosphere. 22.7 half-lives elapse as they're going down to Earth. Again, we're forgetting about relativity for right now. Just what would Newton say? How many of them are going to be left? Well, if one half-life elapsed as they went down, how many would be left? Yeah, so if one half-life elapsed, we would say, well, I started with 1 million of them. Put in my commas so it's easier to read. If one half-life elapsed, I would multiply by 1/2. If 2 half-lives elapsed, what would I multiply by? I'd have to have it again, right? Which would be 1/2 times 1/2, or 1/4. I'm going to write that as 1/2 squared. So if it were 2 half-lives that elapsed, we would do 1/2 squared. If it were 3 half-lives, we'd have to multiply by another factor of 1/2. So I put a 3 up there. If 22.7 half-lives elapse, what number do I put up here? 22.7. Now, you could do this in your calculator as long as you know how to raise something to a power, right? We can do 1,000 times 1/2 with that little raise to the power symbol in your calculator, 22.7, and see what the result is. Do you think it's going to be close to 1 million or close to 0? It's going to be close to 0. When you keep dividing by halves, things get small really quickly. So when we divide by 22, almost 23 factors of 1/2, things are going to be really small. And in fact, if you put it in your calculator, according to my solutions here, you get 0.147 muons. In other words, you have to know how to interpret this. This means sometimes you're on the experiment, you're going to see 0. Sometimes you're going to see 1. Roughly 1 in 10 will you actually see 1, and the other times you'll see 0 coming down. If you perform this experiment 10 times, probably only 1/10 of the time would you even see 1 muon. So they're almost all gone. That means all this radiation is getting created in the upper atmosphere, but none of those muons come down and make it to the ground. If you have a detector that can only detect muons, you're going to see very few signals from the muons. We're going to show tomorrow that with relativity being taken into account, we're going to see lots of muons getting to the ground. And so this is one of the early ways people experimentally tested this time dilation formula, but I'll leave the explanation till tomorrow. All right, questions before we break? And I'm happy to stay and talk about homework. Just so we had great questions on homework yesterday. So those of you who are on Zoom, if you've still got homework questions, hang out. And anybody who's leaving, we'll see you in the tent. Hopefully the rain is pretty much, it was supposed to end sometime shortly after this class, so it's not supposed to be raining by the time we're in the tent, but I think Dr. Kadavid probably already sent you an email. Make sure you bring a seat or something to sit on today because it might well be wet. It rained pretty hard earlier, so who knows if there was some leakage underneath the tent. There might not be a dry patch to sit on, and there's quite a bit of dirt under there, so you probably don't want to be sitting in mud. So if you have to borrow a seat from a chair from a friend because you don't have your own, make sure you do that. Okay, if anybody wants to leave, go ahead and leave, and same to you Zoomers, and if you want to ask questions, just hang out and unmute, and I'll try to take them one at a time. And in fact, let me try to serve some of the Zoom questions earlier, so if you have a homework question on Zoom, shout it out to me.
Yeah.
Royce, okay?
Yeah. Could you go over 3.2A through like all those problems?
Yeah, I think once we start setting it up, we'll get the idea. Let me find my copy of the homework amid all the mess. Oh, and I was supposed to collect homework today too, and I let some people get away without turning it in. So I really do want to post the solutions to chapters 1 through 3. So if you got your homework, there was a stapler up here, so if you didn't staple yours, you can staple them and just make a pile right there in that corner. That would be great. Okay, let me see if I can find my homework questions here. I think somebody asked about this one last time. I've got so many papers here, it's hard for me to find stuff anymore. So there's chapter 1. Here we go. So you said problem what again, Royce? Is it 3.2?
Yeah.
Okay. Right, so this is kind of like the one we did earlier where the light clock is moving, except instead of bouncing up and down while it moves left and right, it's oriented left and right, so it's bouncing left and right as it's moving left and right. So we've got that light pulse moving back and forth. And our goal is to calculate the amount of time, just sort of reading through the statement again. I'm trying to remember who Calvin is. Why is there a Calvin in this problem? Yes, so Calvin is the person watching this move by at speed v, and the question is how long does it take for a full tick to occur according to Calvin? Okay, and so A, focusing on the pulse's movement between the first two images. So between these first two images on here, the light pulse leaves, we can think of this as a bus. So the first moment, the light pulse leaves the back of the bus and it starts heading towards the front of the bus, but the front of the bus is moving all the while. So by the time the light pulse arrives at the front of the bus, that's where that other mirror is, it's traveled longer than the length of the bus. And Calvin is asserting that the length of this bus, according to Calvin, who's watching it go by, is length L. So by focusing on the pulse movement between the first two images, calculate the distance d0, that's this distance here, in terms of c and t0. Well, let's see. The light pulse between this time and this time, the light pulse is going this distance, and it's going at speed c, so I can calculate that distance in terms of c and the time that elapses between these two images.
Yeah, so it'd be d0 equals t0 times c, right?
Yes.
Yeah, I got that one. It was the
Okay.
next couple that were confusing to me.
Okay, so calculate the distance d0 in terms of a different way of measuring it. So this is sort of like in that previous problem, right? We calculated that hypotenuse one way by using the Pythagorean theorem, and then we calculated it another way using just the speed of light. So here we've done the speed of light method. Now we're going to calculate it by focusing on how the mirrored rod is moving. And so the idea is the distance that this light pulse has to move is not just L, it's got to be L plus however far the front of the bus moves during this time period, right? And how far does the front of the bus move? It moves V times T0 because there's time T0 between these two images. So again, we're thinking about how far the light pulse moves in going from there to there, and there's a time T0 between these two images. The distance it moves between those two images is not just L, because it has to move the length of the bus as seen by Charlie or Calvin, I guess, but the front of the bus is moving away from it as it starts heading up there. So it's got to go the length of the bus plus how far the bus front moves between these two images. And I can calculate that's from speed times time, right? The bus is moving at speed v, and the amount of time that elapses between those two images is t0. Does that make sense, Royce?
Yeah.
Okay, so we've calculated d0 two different ways, and we're told to set those two equal to each other and then solve for t0. I believe that's what you're asked to do in C, right? So we would put the t0 over there. That would mean that L is equal to C t0 minus V t0, and then we could factor out a t0, and we'd be left with a C minus V factor. And then finally, I'm going to divide by C minus V to get t0 is equal to L over C minus V. Okay, so that's how you do parts A through C. And you should just write that up to your satisfaction. You're going to see, by the way, the reason we're doing this, it seems sort of out of nowhere for right now, but we're going to see this exact construction happening in the next chapter, which you're reading tonight. So in chapter 6, you'll see this light clock oriented the same way. So I'm trying to get you to think through some of the logic before we get into chapter 6. Okay, so that's A through C. What about D through F? Well, it's the same kind of idea, except now instead of the light pulse moving in the same direction the bus is moving, the light pulse is moving towards the back of the bus, and the back of the bus isn't running away from it, it's running towards it. Okay, and I believe you'll get something like that time interval between the second and third images. After you do the calculation, that minus sign just turns into a plus sign. Do we need to talk about how to approach this D, E, and F? That's just doing the same thing, but between the second and third image.
Right, I think I got it.
Okay, and therefore, the total time that Calvin says for one back and forth tick is going to be T0 plus T1, right? Because it's gone through exactly one tick. It went to the front and then to the back again. So we're going to add these two together. So that's going to be L over C minus V plus L over C plus V. If I've got those numbers correct, or sorry, the expressions correct. And so in G, this is the very final part of the problem, we're supposed to calculate the total time between the time ticks. And because you're going to see this happen in the derivation, I asked you just to get a common denominator between these two things. Do you remember how to get a common denominator between two fractions?
Multiply the denominators together.
Yes. So what I do is multiply this one, top and bottom, by C plus V, right? As long as I do the same thing in the numerator and denominator, we haven't changed it. And I multiply this one, top and bottom, by C minus V. And now I can see the denominators are the same. And if you want, you can stop there, or you can try to do a little bit of simplification, because I've got a common denominator here, and then I could go ahead and add them together, right? I don't know if you know the fact when you have a difference of two squares, that's 1 plus the other times 1 minus the other. So this actually, when you multiply it out, is c squared minus v squared. So that common denominator here is c squared minus v squared. And what's over the top of it? Well, we've got LC plus LV plus LC minus LV. You don't have to do this in your homework because I didn't explicitly ask you for it, but it looks like if you really simplify it over here, can you see where I'm pointing? Maybe not. If you really simplified a lot over here, you would get 2LC over c squared minus v squared. But honestly, once you've found that common denominator, technically you've finished with the homework problem. Is that enough on that one, Royce?
Yeah, thank you.
Do you have anything else?
No, that's it.
Okay. Thanks. All right. Jesse? It's the homework stuff. Okay, 5.3. And let's see. Royce is gone now, so I'm just going to stop the recording on here.